Gaffer on games, like TCP. So let's get creative and work out how we can implement a reliable message system that's better and more flexible than TCP for real-time games. Different approaches. A common approach to reliability in games is to have two packet types, reliable ordered and unreliable. You will see this approach in many network libraries. The basic idea is that the library resends reliable packets until they are received by the other side. This is the option that usually ends up looking a bit like TCP Lite for the reliable packets. It's not that bad, but you can do much better. The way I prefer to think of it is that messages are smaller bit-packed elements that know how to serialize themselves. This makes the most sense when the overhead of length prefixing and padding bit-packed messages up to the next byte is undesirable. Lots of small messages included in each packet.
At the stop sign, turn right onto South Rancho Santa Fe Road.
There are no reliable packets that need to be resent. Reliable messages are simply included in outgoing packets until they are received. The easiest way to do this is to include all unacked messages in each packet sent. It goes something like this. Each message sent has an I that increments each time a message is sent. Each outgoing packet includes the start message I followed by the data for n messages. The receiver continually sends back the most recent received message I to the sender as an ACK, and only messages newer than the most recent ACK message I are included in packets. This is simple and easy to implement, but if a large burst of packet loss occurs while you are sending messages, you get a spike in packet size due to unacked messages. You can avoid this by extending the system to have an upper bound on the number of messages included per packet n. But now if you have a high packet send rate, like 60 packets per second, you are sending the same message multiple times until you get an ACK for that message. If your round trip time is 100 milliseconds, each message will be sent 6 times redundantly before being ACKed on average. Maybe you really need this amount of redundancy because your messages are extremely time critical, but in most cases, your bandwidth would be better spent on other things. The approach I prefer combines packet level ACKs with a prioritization system that picks the n most important messages to include in each packet. This combines time critical delivery and the ability to send only n messages per packet, while distributing sends across all messages in the send queue. Packet level ACKs. To implement packet level ACKs, we add the following packet header: struct header unt16t sequence, unt16t ACK, unt32t ACK bits. These header elements combine to create the ACK system. Sequence is a number that increases with each packet sent. ACK is the most recent packet sequence number received, and ACK bits is a bit field encoding the set of ACK packets. If bit n is set in ACK bits, then ACK n is ACK. Not only is ACK bits a smart encoding that saves bandwidth, it also adds redundancy to combat packet loss. Each ACK is sent 32 times. If one packet is lost, there's 31 other packets with the same ACK. Statistically speaking, ACKs are very likely to get through, but bursts of packet loss do happen, so it's important to note that 1. If you receive an ACK for packet n, then that packet was definitely received. 2. If you don't receive an ACK, the packet was most likely not received, but it might have been, and the ACK just didn't get through. This is extremely rare. Constant time access for the data stored for a given packet sequence number. Constant time removal of entries. You might be thinking, oh, of course. Hash table, but there's a much simpler way. Constant buffer size equals 1024. unt32t sequence buffer size. Struct packet data. Bool ACK. Packet data. Buffer size. Packet data get packet data. unt16t sequence. Constant index equals sequence percent buffer size. If sequence buffer index equals sequence. Return in packet data index. Else return null. As you can see, the trick here is a rolling buffer indexed by sequence number. Constant index equals sequence percent buffer size. This works because we don't care about being destructive to old entries. As the sequence number increases, older entries are naturally overwritten as we insert new ones. The sequence buffer index value is used to test if the entry of that index actually corresponds to the sequence number you're looking for. A sequence buffer value of 0xff indicates an empty entry and naturally returns null for any sequence number query without an extra branch. When entries are added in order like a send queue, all that needs to be done on insert is to update the sequence buffer value to the new sequence number and overwrite the data at that index. Packet data and insert packet data. unt16t sequence. Constant index equals sequence percent buffer size. Sequence buffer index equals sequence. Return packet data index. Unfortunately, on the receive side, packets arrive out of order and some are lost. Under ridiculously high packet loss. 99%. I've seen old sequence buffer entries stick around from before the previous sequence number wrap at 65,535 and break my ACK logic, leading to false ACKs and broken reliability where the sender
turn right into the parking lot, then arrive at your destination.
Highest insert sequence and the new insert sequence, if it is more recent, and clear those entries in the sequence buffer to 0xff. Now in the common case, insert is very close to constant time, but worst case is linear where n is the number of sequence entries between the previous highest insert sequence and the current insert sequence. Before we move on, I would like to note that you can do much more with this data structure than just ACKs. For example, you could extend the per packet data to include time sent, struct packet data, bool ACK, double send time. With this information you can create your own estimate of round trip time by comparing send time to current time when packets are ACKed and taking an exponentially smooth moving average. You can even look at packets in the sent packet sequence buffer older than your RTT estimate. You should have received an ACK for them by now, to create your own packet loss estimate. ACK algorithm. Now that we have the data structures and packet header, here is the algorithm for implementing packet level ACKs. On packet send, 1. Insert an entry for the current send packet sequence number in the send packet sequence buffer with data indicating that it hasn't been ACKed yet. 2. Generate ACK n ACK bits from the contents of the local received packet sequence buffer and the most recent received packet sequence number. 3. Fill the packet header with sequence ACK n ACK bits. 4. Send a packet and increment the send packet sequence number. On packet receive, 1. Read in sequence from the packet header. 2. If sequence is more recent than the previous most recent received packet sequence number, update the most recent received packet sequence number. 3. Insert an entry for this packet in the received packet sequence buffer. 4. Decode the set of ACK packet sequence numbers from ACK and ACK bits in the packet header. 5. Iterate across all ACK packet sequence numbers and for any packet that is not already ACK, call on packet ACK unt16t sequence and mark that packet as ACK in the sent packet sequence buffer. Importantly, this algorithm is done on both sides, so if you have a client and a server, then each side of the connection runs the same logic, maintaining its own sequence number for sent packets, tracking most recent received packet sequence from the other side and the sequence buffer of received packets from which it generates sequence ACK and ACK bits to send to the other side. And that's really all there is to it. Now you have a callback when a packet is received by the other side. On packet ACK, the main benefit of this ACK system is now that you know which packets were received. You can build any reliability system you want on top. It's not limited to just reliable ordered messages. For example, you could use it to implement delta encoding on a per object basis. Message objects. Messages are small objects, smaller than packet size, so that many will fit in a typical packet, that know how to serialize themselves. In my system they perform serialization using a unified serialize function. The serialize function is templated so you write it once and it handles read, write and measure. Yes, measure. One of my favorite tricks is to have a dummy stream class called measure stream that doesn't do any actual serialization but just measures the number of bits that would be written if you called the serialize function. This is particularly useful for working out which messages are going to fit into your packet, especially when messages themselves can have arbitrarily complex serialize functions. Struct test message, public message.
O em 32 TA, B, C. Texto mensagem, A igual a 0, B igual a 0, C igual a 0. Template, Tepnam estreão, Bool serialize, estreão e estreão.
serialized bits, stream, A, 32, serialized bits, stream, B, 32, serialized bits, stream, C, 32, return true, virtual serialize internal, write stream and stream, return serialize, stream, virtual serialize internal, read stream and stream, return serialize, stream, virtual serialize internal, measure stream and stream, return serialize, stream. The trick here is to bridge a unified templated serialize function, so you only have to write it once, to virtual serialize methods by calling into it from virtual functions per stream type. I usually wrap this boilerplate with a macro, but it's expanded in the code above so you can see what's going on. Now when you have a base message pointer you can do this and it just works. Enum test message types, test message A, test message B, test message C, test message num types, message definitions omitted, class test message factory, public message factory, public, message create, int type, switch, type, case test message A, return new test message case test message B, return new test message E, case test message C, return new test message virtual int get num types, const, return test message num types. Again, this is boilerplate and is usually wrapped by macros, but underneath this is what's going on. Reliable ordered message algorithm. The algorithm for sending reliable ordered messages is as follows. On message send. 1. Measure how many bits the message serializes to using the measure stream. 2. Insert the message pointer and the of bits it serializes to into a sequence buffer indexed by message id. Set the time that message has last been sent to -1. 3. Increment the send message id. On packet send. 1. Walk across the set of messages in the send message sequence buffer between the oldest unpacked message id and the most recent inserted message id from left, right, increasing message id order. 2. Never send a message id that the receiver can't buffer or you'll break message X, since that message won't be buffered, but the packet containing it will be ACK. The sender thinks the message has been received, and will not resend it. This means you must never send a message id equal to or more recent than the oldest unpacked message id plus the size of the message received buffer. 3. For any message that hasn't been sent in the last 0.1 seconds and fits in the available space we have left in the packet, add it to the list of messages to send. Messages on the left. Older messages naturally have priority due to the iteration order. 4. Include the messages in the outgoing packet and add a reference to each message. Make sure the packet destructor decrements the ref count for each message. 5. Store the number of messages in the packet and the array of messages included in the packet in a sequence buffer indexed by the outgoing packet sequence number so they can be used to map packet level ACKs to the set of messages included in that packet. 6. Add the packet to the packet send queue. On packet receive. 1. Walk across the set of messages included in the packet and insert them in the receive message sequence buffer indexed by their message id. 2. The ACK system automatically ACKs the packet sequence number we just received. On packet ACK. 1. Look up the set of messages it's included in the packet by sequence number. 2. Remove those messages from the message send queue if they exist and decrease their ref count. 3. Update the last unpacked message id by walking forward from the previous unpacked message id in the send message sequence buffer until a valid message entry is found, or you reach the current send message id whichever comes first. On message receive. 1. Check the receive message sequence buffer to see if the message exists for the current receive message id. 2. If the message exists, remove it from the receive message sequence buffer. Increment the receive message id and return a pointer to the message. 3. Otherwise, no message is available to receive. Return null. In short, messages keep getting included in packets until a packet containing that message is ACKed. We use a data structure on the sender side to map packet sequence numbers to the set of messages to ACK. Messages are removed from the send queue when they are ACKed. On the receive side, messages arriving out of order are stored in a sequence buffer indexed by message id, which lets us receive them in the order they were sent. The end result. This provides the user with an interface that looks something like this on send. Test message message equals test message factory create test message if message